So at a given point, you have the values. So this is the equation, and here the xyz, the C is the concentration at xyz, and the first formula, that is q by 2 pi, and u is a wind direction of standard deviation, that is a coefficient, dispersion coefficient. I'll come to that later. And this equation gives the concentration, the center line of the plume. You know, if you take a cross section of the plume, the center part of the plume will have highest concentration of the pollutants, and this gets dispersed vertically and horizontally. So the center line, so this particular equation predicts the concentration at the center line of the plume at a given point x. And whereas as you move sideways, that is y direction, actually the direction doesn't matter. It can be x, y1, y2, or y like that, either side. So this is the equation that predicts the the horizontal movement of the pollutants. If you are interested at y2 or whatever, you can. This is the equation for the horizontal movement, and this is the equation for the vertical movement of the pollutants. So this sigma y and sigma z, the coefficients, are actually arrived based on the the diffusion parameters, which is like it is available in all the air pollution textbooks. We can based on the atmospheric stability, we can actually get the coefficient values, which I'll come to that later. So you can have all the three equations at whatever is the desired location. For example, you may be interested only in the center line of the plume. So this is the formula that is used for the center line at a given downward wind point. And for example, this is a small example. A factory emits 20 gram per second of sulfur dioxide at height 8. The wind speed is 3 meters per second. At a distance of 1 kilometer downstream, the sigma y and sigma z are 30 and 20 meters. This 30 and 20 meter is normally given. Otherwise, we can, based on the atmospheric stability, or it can be easily taken from the graph. And I'll show you that graph. So what are the SO2 concentrations? This is a question. What are the SO2 concentrations at the center line of the plume at a point 60 meters to side and 20 meters below the center line? So the concentrations at the center line also is required, 60 meters to the side and 20 meters below the center line. So here is the values, and you apply here, and you get try to calculate it at 60 and 20 meters, and you get the values here. That is, this is the value for the at a given point at x, whereas in the x, this is a ground concentration, so the z and y will be 0, 0. So this is the concentration at the ground level at the desired point, whereas the center line is y and they are 0 because we are only measuring the ground level concentration using this equation. So as I told you, the valuation of standard deviation of y and z are actually based on the atmospheric stability conditions, and let us I can show you the stability. Stability class is A, B, C, D. If it is extremely unstable, it is A, B, C, D, and E. So how you come to this conclusion? This is like based on the solar the solar elevation, that is the solar radiation, and the time when the measurement or the Gaussian plume is applied. For example, if it is above 60 degree from the horizon, if may be a little difficult to understand, but you can consider that probably during the um afternoon time you get very high solar radiation. So the solar inundation, or that is like, if the angle is above 60 degrees, then it is considered as strong. So based on these classes, it is whether it is between the solar radiation, and also again the wind speed. So based on these two, there have been, we can find out the, for the x and y is that. So here you can see the, from the figure 4 to 7, x is 500 meters. So that this is the diffusion parameter, which is arrived using this table, that is the stability class, whether the atmosphere is stability, and how do you define the, and this is another equation that is being used to calculate the effective stack height, the plume rise, and this is like, again based on the, the stack velocity, then the heat emission rate, and the wind speed. So based on this, we can calculate the delta H, that is the plume rise. So here, here there are some of the examples of, if it is a neutral atmosphere, this is the stability coefficient. So here, this is a sort of atmosphere where there is an inversion layer. This is the lapse rate. As the altitude increases, the temperature decreases, but at some point of time, there is a temperature inversion. As you go higher and higher, there may be an increase in temperature. This is normally it is called as inversion layer. And since the layer is very warm, the pollutants cannot disperse vertically, so that it gets trapped here in this layer. So, and similar thing occurs in the valley also. And this is how the plume behaves based on the lapse rate, that is the adiabatic lapse rate and the environmental lapse rate. R is the environmental lapse, and the vertical movement of the plume is affected by the lapse rates. And there is a dry adiabatic lapse rate and wet adiabatic lapse rate. And if there is an inversion in temperature, and these lapse rates are highly affected, and it determines the movement of the air pollutants. So this is plume behaves if like this, if there is adiabatic lapse rate is more or less equal to the environmental lapse rate. And if there is an inversion, temperature inversion, then the pollutant doesn't come down, and it remains like, it is called as fanning. So this is how pollutant behaves during the inversion. And this is again fumigation, where the layer of which we saw earlier, where the temperature suddenly increases after some high altitude, and the pollutant, there is a vertical movement, or the vertical dispersion is totally affected by this phenomenon. And this again is like, if the temperature or the inversion happens at the ground level, then this sort of behavior can be expected. So, but the Gaussian model does not take into account all this. It assumes that source pollutant emission rate are constant, steady state, constant wind speed, constant wind direction, and the atmospheric stability class is also taken as either one thing, that is stability class A or B. It is not that a plume experiences all these classes. And pollutant mass transfer by primarily due to the bulk air motion in the x direction, and it doesn't take into account if there is a kind of obstruction or a terrain disturbance. And no pollutant chemical transformation occurs, that is pollutant A and B doesn't react each other and form another chemical, and it takes that everything remains constant. And so all these conditions, like the stability at one point is different and atmospheric stability at another point is different, and the Gaussian plume model at times does not take into account. And now there are some more Gaussian plume models which also considers the terrain correction, Egan terrain corrections, like if there is a mountain nearby, so you can apply a different equation which corrects the terrain, and also the building. If there is a building, then there could be a swirl wind or something which would affect the plume behavior. So this is also taken into consideration in the recent models. Now coming to the receptor models, as I told you earlier, receptor model takes the ambient concentrations in a given receptor location, and it tries to identify the source contributions or the source profiles. So this is mainly based on the mathematical models and the statistical models. So in this case, the input parameters like the ambient concentration CI, and then uncertainties, source profiles and uncertainties, ambient concentrations and uncertainties, source profiles and uncertainties. Output is the source contributions and uncertainties. So here, the chemical mass balance is one of the commonly used receptor models. And this model quantifies the contribution using the chemical signatures, characterizing the source types rather than the contribution from individual emitteries. So the CMB model uses the chemical composition of the ambient pollution samples to estimate the contribution of different source types to measured pollutant concentrations. That is, actually you get a set of values in a location, set of pollutants or the levels or the concentrations of pollutants, and we try to identify or match with the source profiles which are already available, and then finally come to a conclusion that this could be from these sources. For example, if you find the sulfur dioxide in a location as 80 microgram per meter cube, and based on the model, we can identify that this particular mass is from the industry or the kind of emitting sources, probably a coal-fired power plant or something like that. So actually these are the instruments that are being used at a location to monitor the ambient air quality. It may be PM10 or PM2.5 or sulfur dioxide, anything. These are the samplers that are being used to find out the concentrations in a location. And these are the source profiles. The source profiles or the emission inventory. These are like from the emission sources we can identify, for example, if there is what kind of sulfur dioxide or what kind of what amount of nitrogen dioxide or what amount of particulate matter is being released from this kitchen or from an industry or from a vehicle. So these are all actually inventoried, and these are used as a source profile. You can see the emission testing, and based on this can serve as an input parameter. So this is a typical the kind of graph which is being generated in the chromatography mass spectrometry, as if a gasoline engine, these are the compounds that are emitted out from the gasoline powered vehicles, and these are the kind of chemicals or the carbon compounds and their concentrations, or their at for example, even the source profile is available for the road dust. If you have all these compounds in your ambient concentration, we can figure out that this could be probably from the road dust. Or if you find this set of compounds in your receptor location, we could figure out, or we could conclude that maybe this is from the diesel source. So this is how a chemical mass balance works out. You can see like the different sources are given here: industry, transportation, vegetation burning, geological, marine, secondary organics. So using a chemical mass balance model, we can identify from the given concentration at a location, we can identify these are all could be the probable sources. For example, in Asia, the 40 percentage of sulfate is from the sulfate is secondary ammonium sulfate from the PM, and then only 3 percentage is from the transportation, and 10 percentage of the PM 2.5 mass is from the industry. So this chemical mass balance model can predict the source concentrations like this. It's very useful to determine the sources in an area, and appropriately the management measures can be taken using this data. A similar such model is positive matrix factorization, and this is also again a multivariate analysis tool. Almost it also gives the same kind of results. The EPA, the Environmental Protection Agency US, has developed this model, and actually this model needs huge, can be applied when there is a huge set of data, and it normally requires a large data, and from the large data again it can identify the same kind of source profiles, and we can find out based on the ambient concentrations, and we can derive the source, whether it is industry or road dust or power plants. We can easily determine the sources by using the PMF analysis, and it is the software is available in the US EPA website. You can download and attempt computing the sources by using a different set of data. And the source contributions are used to determine how much each source contribute to a sample. For example, this is again the PMF analysis can also easily find out, even within the source, it can even find out what sort of source, whether it is from the tire wear or the resuspension or exhaust emissions. So the emissions depend upon all these parameters are taken into consideration while calculating the contribution from each source. So this PMF gives a kind of values like this. So based on this this value, we can come to it. It gives different factor one from a set of data. We get the factors like this: factor 1, factor 2, factor 3, and it can be maybe the factor 1 can be the vehicular pollution that is given in blue. In this each circle different denotes different places. For example, in place A, the pollution is mostly from the vehicular emissions, and here also it is likely from the vehicular emissions, whereas the orange can be of industry and the green can be of agricultural burning. So PMF analysis gives an idea of each and every source, and it also the quantifies, or it gives in percentage how much is the quantity of pollutants from each sources. So again, another mostly widely used model is the principal component analysis. This is again a statistical tool. It is also used for data reduction. The statistical method is used, it is actually based on the covariance matrix from the given set of data. For example, in a location, if you measure ambient air quality, and also if you measure different kinds of heavy metals, for example, copper, lead, iron, chromium, cadmium, etc. And if you try to analyze using a PCA, the it like the output will be like a set of it. The PCA gives you a set of values, and from which we can interpret the sources. That is, in a system with multiple input variables, this approach is used to determine the variables with greater eigenvalues, that is, eigenvalues more than one, and further identifying the core problem. For example, this is like a PCA identifies a set of components, that is, component factor 1 may be one component, one group of components, factor 2 may be another group of component. And based on this separation, or based on this identification, we can come to a conclusion that this phenolphthalein or benzoyl, this set of combination is from the diesel vehicle, and this set of combination is from the LPG vehicle, or this set of combination is from the kitchen. So this PCA is an easy method which is being widely used to identify the source. So that's all we have for today, and this is the most commonly used models for the air quality. Thank you.